At 4 in the morning on March 28, 1979, 3 Mile Island Unit 2 lost the flow of water that carried heat away from its steam generators. The turbine tripped. The reactor shut down automatically. Pressure surged inside the primary cooling system, and a relief valve opened exactly as designed. 12 to 15 seconds later, the pressure had fallen far enough that the valve should have closed. In the control room, its indicator changed state. To the operators, that meant the valve was closed, but the mechanical valve had jammed open. For the next 139 minutes, reactor coolant escaped through a path the control room believed was sealed. By the time that path was finally isolated, the core heat-up was already underway. The contradiction at the center of the accident was simple. The system reported the command it had sent, not the result it had achieved. The component was a pilot-operated relief valve mounted above the pressurizer. When system pressure rose too high, an electrical solenoid commanded the valve to open and release steam and water into a drain tank. When pressure returned to normal, the solenoid de-energized and the valve was supposed to reset. The control room light followed that electrical signal. It could tell operators that the command to open had ended. It could not confirm that metal had moved. The seat had sealed or flow had stopped. During the accident, the signal said one thing and the hardware did another. There was no direct position sensor closing the information loop. Other clues existed: pressure, temperature, and the behavior of the drain tank, but they were scattered across a control room filling with alarms. A one-bit indication collapsed two different facts into one. No longer commanded open, became physically closed. The stuck valve kept releasing coolant, but the most prominent level reading appeared to show the system filling up. 1 minute into the event, the pressurizer level began rising rapidly. Between 4 and 11 minutes, it went off-scale high. Operators had been trained to avoid filling the pressurizer completely, so they reduced the high-pressure injection that was automatically adding emergency cooling water. The reading was real, but the picture built from it was wrong. Steam bubbles and voids were forming elsewhere in the reactor coolant system. The reactor vessel had no direct instrument showing whether water still covered the core, because under normal operation, it was assumed to remain full. High level in the pressurizer did not mean high inventory everywhere, yet the interface offered no clear view of the missing water. Coolant was leaving through the open valve, while operators, trying to prevent an overfilled system, restricted the water replacing it. The timeline shows how a recoverable malfunction became core damage. At 30 seconds, all 3 auxiliary feedwater pumps were running, but closed discharge valves prevented water from reaching the steam generators. Those valves were opened at 8 minutes. At 15 minutes, continued discharge from the stuck relief valve ruptured a disc in the drain tank. After 1 hour and 15 minutes, vibration led operators to stop the coolant pumps in one loop. 25 minutes later, they stopped the pumps in the other. With voids inside the system, natural circulation could not carry heat away. Between 1 hour 45 and 2 hours, the core heat-up transient began. Only at roughly 2 hours and 19 minutes did an operator close a separate block valve and isolate the leaking path. The original relief valve had needed about 15 seconds to become dangerous. The plant needed 139 minutes to prove that it had never closed. 3 Mile Island was not caused by a single operator, a single light, or a single broken valve. The Nuclear Regulatory Commission identified a combination of equipment malfunctions, design problems, and human error. Auxiliary feedwater was initially blocked. The relief valve stuck. The display represented its control signal instead of its physical state. The level instruments encouraged a misleading mental model. Procedures and training did not prepare the crew to recognize this particular loss of coolant accident. Each action made sense inside an incomplete picture, and each removed another layer of protection. About half of the reactor core eventually melted. Yet the containment largely performed its purpose, and the NRC says the small radioactive releases produced no detectable health effects on plant workers or the public. The physical outcome was severe. The public health outcome was far smaller than the fear surrounding it. After 3 Mile Island, the nuclear industry changed operator training, emergency procedures, control room design, and the way safety systems reported their condition. Relief valves needed reliable, unambiguous indication of actual position or flow, not merely evidence that a command had been issued. That lesson reaches far beyond nuclear power. A green light can mean the request was sent, the motor received voltage, the database accepted a write, or a remote service returned success. None of those proves that the physical or business outcome happened. Critical systems need closed-loop confirmation, command, response, measured state, and a clear warning when those disagree. At 3 Mile Island, the valve failure opened the path. The information failure kept it open. This is fault cascade, where the most dangerous gap may be the distance between what a system was told to do and what it actually did.